Hello, today we are solving a problem on the motion of a body thrown at an angle to the horizon, and let's get started. The quarterback can throw the ball in different ways. The graph shows two trajectories in which there are two throws. There's the up pass, which is trajectory number 1, and the down pass, which is trajectory number 2. The upper pass is made at a velocity of 21.5 tenths of a meter per second, and the time of flight of the ball is 3.97 hundredths of a second. What is the angle of throw in this case? Second question. A low pass has a throwing angle of 25 degrees. What is the initial velocity of the projectile and what is its time of flight? So we will need to investigate two types of throwing by this person, player, and accordingly our task now is to record the data and see how to determine the values we are looking for. What do we know for the first trajectory? We know that here the initial velocity in the first case is 21.5 meters per second, and the time of flight is 3.97 hundredths of a second. For this situation, we must determine the angle of throw. Let's denote the throwing angle by the letter alpha. So for the second case, we know that the throwing angle is 25 degrees. And we need to determine the initial velocity of the projectile and the time of flight of the projectile in the second case. Let's look at the first situation. Analyze what we know and see how we can determine the value we are looking for. In this case, it is the angle of throwing the ball for an overhead pass. What do we know for this situation? We know the time of flight, we know the initial velocity of this throw, and for this we need a formula that will tie all these quantities together. In order to solve this problem, we will need a formula that we can use to calculate the time of flight. Let's remember it. We derived it with you in our theoretical lesson. So, let's write down the formula by which this value is determined. Double the product of the initial velocity for the first case by the sign of the angle of throw and divided by the acceleration of free fall. This is exactly the formula we received, and we see that here the unknown quantity is the sine of the angle of throw. Let's express it from here. So, the sine of alpha would be, this is g times t1 and divide by twice the initial velocity. Okay, we've got the formula. Let's put a value on it. So g is 981 times the throwing time, 3.97 hundredths, and divide by twice the initial velocity. Here you get the top and bottom dimensionality of the velocity, which means it's going to shrink, so that leaves the dimensionless value. Actually, sin alpha is just some dimensionless number. So, well, and accordingly, this sine value is 0.9057. And if we calculate the sine value for a particular angle, this angle will be 65 degrees. That is, this is the angle at which the throw was made in the first situation. As for the second case, here we see that the angle of throwing is 25 degrees, and our task is to determine the initial velocity and time of flight. What do we need to know for this? Here we see that both balls landed at the same point. This is one of the properties of throwing at an angle to the horizon. When the two angles total 90 degrees, then the body will land in the same point. That is, their range of flight will be the same. This is the parameter that we denote by the letter L, and thus we can equate the range of the first throw and the range of the second throw in order to find the initial velocity for the second case. Let's do it. Let's do that. Now the range, I remind you, is determined by the formula. The square of the initial velocity times the sine of the double angle and divide by g. So our task is to write the range for the first case and for the second case and equate these expressions. Then we get that the initial velocity of the first case is squared times the sine of 2 alphas divided by g, equal to the square of the initial velocity in the second case times the sine of the 2 betas and divide by g. That's it, we have got this expression from where we can now find the initial velocity for the second case. It can be seen that here g can be reduced and we get the expression for the given velocity. Immediately we write the expression through the square root. We have obtained the final formula, it remains only to put the numerical value. So the square of the initial velocity is 21.5 tenths. Squared times the sine of 2 alphas. We've got an alpha of 65 degrees, so that would be the sine of 130 degrees. And divided by the sine of 2 betas, that's the sine of 50 degrees. And accordingly we get a velocity value approximately equal to 30 meters per second. Well, in order to calculate the time of flight for the second case, we already have a ready expression. Let's use it at once. That is, it is the doubled initial velocity multiplied by the sine of the angle of throwing and divided by the acceleration of free fall. And let's substitute the value. 2 times 30 times the sine of 25 degrees. So the time of flight is approximately 2.6 seconds. So we have all the answers to our questions. And we've successfully solved this problem. This problem is indicative of the fact that indeed sometimes there are cases when at different angles of throwing there is a fall to one point, and it is possible even without making any calculations to connect the two trajectories. Take advantage of this and use this knowledge in practice. See you soon. Goodbye.